Okay, continuing our look at limits. We're going to look at one-sided limits where we're not approaching from both sides, but we're only approaching a value from either the left or the right. So if we have the limit of f of x as x approaches c with a little minus sign there, that indicates that we are approaching from the left, okay, from the negative side. And if we have the limit of f of x as x approaches c with a plus, that indicates that we are approaching that value of c from the right-hand side. Okay? So looking at evaluating a limit only approaching from one side rather than moving in from both sides at the same time. Okay? So if we look at this function 2x, the absolute value of 2x divided by x, and we look at approaching x strictly from the left-hand side. Okay. That means we're only looking at putting in negative values. Okay. So if I were to completely put in negative values, if we were to look at the graph of the function of absolute value of 2x divided by x, okay, what we would see would be something along these lines. Okay. The graph looks something like this. Okay. Kind of missed the mark there, but that's going to be the point 0, 2, and it's going to be coming this direction from the point 0, negative 2. Okay. So the limit of f of x as x is approaching from the left, as I'm approaching from the left-hand side, all of my values are at negative 2. But as I'm approaching as x is approaching 0 from the right-hand side, everything is at positive 2. Okay? So as I approach from the left and I approach from the right, I'm not actually approaching the same value, which, as we saw before, is one of the situations where we would say that the limit does not exist. Okay? Which brings us to the definition for existence of a limit. Okay? The limit of f of x as x approaches c is equal to L if and only if the limit as it approaches from the left equals L and the limit as we approach from the right equals L. Okay? So if they don't both equal the same value, the limit at c does not exist. So the left-hand limit and the right-hand limit have to be the same value in order to have existence of our limit. So here we have another function, okay, and we're trying to figure out the limit of f of x as x approaches 1. So in order to do that, we're going to have to figure out the limit as x approaches 1 from the left, and we're going to have to find the limit as x approaches 1 from the right. Okay. We need to find both the right and left-hand side limits. So if we look at the first part, for x is less than 1, we have 4 minus x. Okay. So I'm not actually defined at 1, but if I were to put in 1 for x, I would have 3, which means I'm going to have an open dot at 3. If I put in 0 for x, I'm going to be at 4. Negative 1 is going to give me 5, so the graph is going to go linear. Okay. If we look at the second part, if I were to put in 1, I'd have 4 minus 1, which is still at 3. If I put in 2, I get 8 minus 4, so 2 is going to be at 4. 3 is going to be 12 minus 9, so 3 is back at 3, and 4 is going to be at 0, and we're going to have this quadratic shape. Okay. So the limit of f of x as x is approaching 1 from the left. Okay. So as I'm approaching from the left, I'm following this piece of the graph, and that appears to be going towards a value of positive 3. as I'm approaching from the right, I'm now following this parabolic shape, and as my x's are approaching 1, my y values again are approaching the value of 3, which tells us that the limit of f of x does exist and that that limit is equal to 3 because we had 3 in both cases. If those numbers would have turned out to be different values, then we would say that the limit does not exist. So get another one. Okay, maybe try this one, maybe pause the video and try this one on your own. But again, we need to look at the limit of f of x as x approaches 2 from the left, and what is the limit of f of x as x approaches 2 from the right. Okay. Well, less than or equal to 2, I have the graph of x minus 1. So when x is 2, my y is going to be 1. Okay, and that is defined there, so it will be a closed dot. When x is 1, then I'm going to be at 0. When x is 0, I'm going to be at negative 1. So my graph heading back this way in a linear fashion. Okay. For x is greater than 2, I have the graph of 2x minus 3. So if I were to think about the second part putting in a 2, I'd still end up at positive 1. If I put in 3, I'm going to have 6 minus 3, which is 3. If I put in 4, I'm going to have 8 minus 3, which is 5. Okay. So the graph is going up this direction now, just changing the slope. Well, what is the limit of that function as x is approaching 2 from the left-hand side? As I'm coming in this direction, I appear to be going towards a value of positive 1. As I'm coming down here, coming in towards x equals 2 from the right, again, I am closing in on a value of 1. So the limit of f of x as x approaches 2 would be equal to 1. Okay. So now let's start looking at some difference quotients. Okay, we had the difference quotient before we started into chapter 11. The f of x plus h minus f of x all divided by h, but now we're going to take the limit of that as h approaches 0. Okay. So as I come down here and evaluate my function, f of x equals 5 minus 2x, the f of x plus h is going to be 5 minus 2 times x plus h minus the f of x, which is 5 minus 2x, and that's all divided by h. And we're going to take the limit as h approaches 0 of that expression. Okay. So when we start to simplify, we'll have 5 minus 2x minus 2h minus 5 plus 2x. Okay, kind of skimming off the page here a little bit. Divided by h. Well, we can see that our 5's going to subtract out, our x terms are going to subtract out, and I'm left with the limit as h approaches 0 of negative 2h divided by h, but now my h's also divide out, which means I'm left with the limit as h approaches 0 of negative 2. Well, there is no more h, so that's just going to give me a value of negative 2. And remember, we talked early on about that limit of the difference quotient really representing the slope of the function, the slope of the curve at some given value. In this case, we're talking about what is the slope at 0. Well, if you go back to the function, the original function was a linear function, and look at the slope. It's negative 2. Turns out to be the same thing. Okay? So remember, with linear functions, our difference quotient, when we take the limit, we should end up with the same value as the slope. Alright, so let's try one that's not a linear function. Okay, so we want to take the limit as h approaches 0 of f of x plus h, which would be the square root of x plus h minus 2, minus f of x divided by h. Okay? Well, here's where we're going to have to rationalize the numerator. So now this is where it gets messy. So we're going to multiply x plus h minus 2 plus square root of x minus 2 over square root of x plus h minus 2 plus square root of x minus 2. Okay? So we're going to rationalize here. So what do we end up with? We have the limits as h approaches 0. Our numerator, remember this is the a plus b, a minus b pattern. So I end up with a squared, which is just going to be the x plus h minus 2, minus b squared, which is going to be the x minus 2, divided by h times, I'm going to leave those radicals just the way they are, and I'm going to leave this as a product. Okay? Because what's going to happen here is our x's, I'm going to have x, and this is going to be a minus x, so that's gone. This is going to be a plus 2, so that minus 2 is going to be gone. Okay? And then all I'm left with is the h, so the h's are going to divide out, and I'm really left with nothing more than 1 over the square root of x plus h minus 2 plus the square root of x minus 2. Okay? So as h is approaching 0, what do I end up with? Well, as h approaches 0, I end up with the square root of x minus 2 plus the square root of x minus 2, which is 1 over 2 square root of x minus 2. Okay, so there is our limit as h approaches 0. Okay? So we will do some more work with these things in class tomorrow. See you then.